Hello, math humans. We're going to do 3.4a today. We're going to be solving log and exponential equations. Our objectives are that we're going to do some math. Woohoo! We're going to switch between log and exponents forms to help us solve equations. Alrighty, so we're going to do some examples today, and then we will do more examples tomorrow. Oftentimes, when I am solving log or exponential equations, I just bounce back and forth between the two forms. So this one is going to be an exponent form. I could solve this with logs. I could take the log of both sides. Let me show you. So I could say x log 2 is equal to the log of 32, and x is the log of 32 divided by the log of 2, and I would get 5. So that's a lot of work. I can just use my 1-to-1 property, so 2 to the x is equal to 2 to the 5th, and then I write x is equal to 5. Ta-da, done. All right, example 2, I'm going to have the natural log of x minus the natural log of 3 is equal to 0. The first thing that I would do is use my properties of logarithms to make one statement is equal to 0. And then if I go back to exponent form, e to the 0 is equal to x over 3. Well, e to the 0 is equal to 1, and then I can cross multiply, so x is equal to 3 times 1, which is 3. So that was pretty nice. Example 3, I have 1/3 raised to the x is equal to 9. And this one I'm going to use the 1-to-1 property also because I know 3 and 9 are related. So I'm going to change this to be 3 to the negative 1x is equal to 3 squared. This side becomes 3 to the negative x because a power to a power is multiply. The bases are the same, so I get negative x is equal to 2, or x is a negative 2. Okay. Next example, example number 4, we're just cruising right along. I'm going to have the natural log of x is equal to a negative 3. This one is starting in log form, so I'm going to go back to exponent form. The base is e, so e to the negative 3 is equal to x. Push buttons on my calculator, and I get 0.498. Remember that when we report numbers, we always do that to the third decimal place. Sorry, bad grammar. The fifth example, I'm going to have e to the negative x squared is equal to e to the negative 3x minus 4, and it looks really scary, but it's actually really pretty straightforward because the bases are the same, so the 1-to-1 property kicks in. So I'm going to solve the baby equation at the top, and I get a negative x squared equals a negative 3x minus 4. Now it's just a simple quadratic, which means everything has to go to the left-hand side. So I get a negative x squared plus 3x plus 4 equals 0. I'm going to factor out a negative, so x squared minus 3x minus 4 is equal to 0. Now I can factor x minus 4 and x plus 1 is equal to 0, so x is equal to 4 and a negative 1. So that was actually pretty easy. All right, example 6. I have 3 times 2 raised to the x is equal to 42. Anytime you solve an equation, the goal is to isolate the x term. So I'm going to divide both sides by 3, so 2 to the x is equal to 42 divided by 3, and that's 14. So now I notice that I have the equation 2 to the x is equal to 14, and 14 is not a power of 2. So now is when I'm going to take the log of both sides. When I take the log of both sides, remember by the properties of logarithms that the exponent goes out front, and I'm going to choose the natural log. For me, it's because I'm a wee bit lazy, and natural log has one less letter to write than log. And again, all I did is I took the log of both sides, and I used the property of exponents to pull that guy out front. Now I'm going to solve for x. X is equal to the natural log of 14 divided by the natural log of 2, and then this is 3.807, and that value would have come from my grapher. Alrighty, I have two more examples for us today. Nice short day. So example 7, I have the log base 6 of 3x plus 14 minus the log base 6 of 5 is equal to the log base 6 of 2x. The first thing to notice is all of the logs have the same base. So now I'm going to use the properties on this side to put those two terms together. So this is the log base 6 of 3x plus 14 divided by 5 is equal to the log base 6 of 2x. Now the one-to-one property kicks in because the logs are the same on both sides. So now I get 3x plus 14 over 5 is equal to 2x. I'm going to cross multiply. 3x plus 14 is equal to 10x. Combine like terms, so I'm going to get 7x is equal to 14 because I took the 3 to the other side. Alrighty, divide both sides by 7, and I get x is equal to 2. That's pretty nice. Alright, I have one more example, so we're going to put it right up here in the corner. Example 8. So I have 2 to the 3 2t minus 5 minus 4 is equal to 11. Again, the goal is always to isolate the term that has the variable in it. So the first thing that I'm going to do is I'm going to add 4. So I get 2 times 3 to the 2t minus 5 is equal to 11 plus 4, which is 15. Now I'm going to divide by 2. 3 to the 2t minus 5 is 15 over 2. And I'm just going to leave it like that. You could make it 7.5 if you wanted. Because this is an exponent form, I am going to go back to log form. And when I take the log of both sides, the property of exponents kicks in. And this 2t minus 5 is going to go out front. So in parentheses, 2t minus 5, natural log 3 is the natural log of that's a 5. The goal is still to solve for t. 2t minus 5 is the natural log of 7.5 divided by the natural log of 3. Add 5. 2t is, and don't use your calculator until you get all the way to the very end so that you don't generate error. And t is going to equal this long mess of terms divided by the natural log of 3 plus 5, the whole kit and caboodle, divided by 2. And if you do all of that math in your grapher in one fell swoop, you get that t is equal to 3.417. All right, that is it for today. That was some really fast examples. I will see you soon.